Okay, we're going to look at this eighth tutorial on Lenz's law, and we're going to develop Lenz's law in this tutorial. I'm going to share my screen and okay. Um, we start with a copper ring, a copper wire loop that's placed in a uniform magnetic field. We can see that it's uniform because the field lines are evenly spaced here. And we want to determine whether there would be a current, an induced current, through the wire of the loop in each of the cases below. And we want to use that magnetic force. You remember the Lenz force was that the magnetic force had a magnitude that was equal to QVB sine theta. Okay. And so using that magnetic force um, and using the cartoonish model where we think of that wire loop as a hula hoop, a plastic hula hoop that contains positive charges. And when we move the hoop, we're moving the charges. Well, we're going to start, first of all, with the hoop stationary. Okay. And if the hoop is stationary, then this formula, QVB sine theta, well, the V is zero. And so that's easy. Now, if the hoop is moving to the right, all of the charges are moving to the right. But that's also the direction of the magnetic field. And so now my Lorentz force equation, the theta is going to be 0 degrees, and the sine of 0 degrees is 0. So this then goes to 0. That's a 0. If the loop is moving to the left, well, again, my magnetic force equation, QVB sine theta, theta is now going to equal 180 degrees, and the sine of 180 degrees is also 0. So I don't get a current generated in any of those cases. Now, in class, when we talked about Faraday's law, um, Faraday taught us that what changed, what mattered was the change in the number of field lines through the loop. And that's what generated this invisible battery, this induced battery that drives the induced current. And in all three of these cases, we're not changing the number of field lines through that loop. So let's change things up now. Now, instead of a uniform magnetic field, it's going to be a magnetic field that changes. It's weak out here and it's strong close to this solenoid. Now we can see that this solenoid is acting like a little bar magnet with the north on the right and the south on the left. And so these field lines are coming into that south pole there. Now, um, we're asked to use this same uh, magnetic force equation to determine whether there would be a current through the wire loop in each of these cases. And again, we think of that wire loop as a hula hoop, plastic tube carrying charge carriers. Well, if it's stationary, again, if V is equal to 0, the magnetic force would be 0, so there would be no current. But what if that uh, What if that loop was moving to the right? Well, I'm going to redraw the loop. I don't draw very well, you know that, but I'm going to do my best. I'm going to do my darndest. Okay, I tried. Now, if I'm moving the loop to the right, the motion of the charge carriers is also to the right. And that's in a magnetic field that is pointing towards this South Pole. And this is what we did in lecture. Okay. And what we find is that uh, there is a magnetic force. And so there would be current. And if the loop is moving to the left, let me draw that loop again. Well, now the charge carriers are moving left in the magnetic field that is again towards the South Pole. So these are magnetic field directions. Okay, so again, there will be current. When a current is caused to flow in a loop due to an external field, we say that this induces a magnetic flux. In other words, that current is going around the loop, and we know that whenever current's going around a loop, that looks like a bar magnet, and there's going to be a magnetic field due to that current that passes through the middle of the loop. The direction of the induced magnetic flux, the field lines, is in the same direction as the direction of the induced magnetic field at the center of the loop. The size of the induced magnetic flux is proportional to the strength of the induced field at the center. In other words, stronger field, more field lines, more flux, more flux. So for each case, and we've got two of them, for each case that there is an induced current, determine the direction of the current through the wire of the loop. Okay, so let's take the two cases individually. This would be when it's going to the right, and this would be when it's going to the left. Okay, well, when it's going to the right, if I use right-hand rule number one, I reach in the direction of the motion and I wave in the direction of the B field, and my thumb is into the page at the top. And if I do the same thing at the bottom, it would be out of the page. So the current comes out the bottom of this ring, goes up the front of the ring, and then away from us at the top of the ring. Um, and so the direction of the current would be uh, up the front. Now, if I do it for, oh, can't see that. If I do it for the case where it's moving to the left, right-hand rule tells me that it's out of the page at the top and into the page at the bottom. And so that means the current, the induced current, is going to be down the front. So I would write down the front. Okay. Now, what about the direction of the induced magnetic flux of the loop? Well, now I'm going to use right-hand rule number 3. Because that current that's induced is going in a circle, I'm going to use the curved part of my right hand to represent that current. And then the straight part of my right hand is going to point in the direction of the magnetic field and hence the magnetic flux. And so in the first case, it's going to be uh, to the left, and in this second case, it's going to be to the right. Okay, so in this case here, this is going to look like a little bar magnet with the north side here and the south side there. And here it's going to look like a little bar magnet with the south side here and I'm sorry, the north side here and the south side here. Okay. Um, so let's let's use those ideas where the whole point of this page is to set you up for the second page, which is the most important page of this tutorial. In this case, we're going to redo what we just did, only now the field lines are coming out of some uh, source and spreading out. And so that might be the north pole of a bar magnet or the north pole of a solenoid, something like that. And okay. And we're asked to indicate the direction of the induced current through the wire of the loop um, using the same technique that we did before. Um, well, now we've got this loop moving to the right, and it's moving in a magnetic field that is away from the north. And so if I use my right hand rule, reach in the direction of the velocity, swing in the direction of the B field, this time it's going to come out at the top and go in at the bottom, meaning that it's going to go down the front. And if I have the case where the loop is going the other way, away from the North Pole, in a magnetic field that is pointing away from the north, if nothing else, this tutorial is giving you some practice using right-hand rule number one. And remember, it's good to turn your page so that you can reach away from your body so that you don't hurt yourself. Okay, so I reach in the direction of the velocity. I turn my wrist so I can wave in the direction of the B field, and my thumb is pointing into the page at the top and out of the page at the bottom. And so in this case, the induced current is going to go up the front and down the back. Whereas in the first case, A, it went down the front and up the back. Okay. Now, we are going uh, to help us understand um, this idea, we're going to divide up flux into two flavors. We're going to talk about the external magnetic flux, and that's due to everything that's not the copper loop. In this case, it would be due to that North Pole. And we can think of that magnetic flux as a vector that indicates the total number of field lines through the loop due to the external field. Now, in truth, it turns out that is not a vector, it's a scalar, and there are some very complicated uh, right-hand rules to figure out whether it's positive or negative. We have enough minus signs and we have enough right-hand rules, okay? I find that if we treat magnetic flux as a vector, it's so much easier. And so if the field lines are going through this loop to the left, I would say that the flux is to the left, okay? And the more field lines that go through that loop, the bigger that vector would be to the left. The direction is simply the direction that the external field passes through the loop. Increasing the external field strength, therefore increases the external magnetic flux through the loop because you've got more field lines. So this is where we put it together. We're going to consider case A and case B, and in both cases, we would like to indicate the initial and final external magnetic fluxes through the loop. So in other words, what direction does the magnetic flux due to this North Pole go through the loop, and how many field lines make it through the loop? Well, when I'm far away, I only get a few field lines going through that loop, but they go through to the left. And then when it gets closer, more of the field lines are going to be going through the loop. The magnetic field, when I get closer to that North Pole, will be stronger. Well, in case B, we're going the other way. We're going away from that strong magnetic pole. And so we're going to start with lots of field lines going through the loop to the left. And when it gets further away, there would be fewer magnetic field lines. Now, in this case, we would like to indicate the direction of the change in external magnetic flux. Okay. Now, you remember we talked about change in Physics 105 and also earlier this semester. Um, if you want to know what the weather is like, you stick your head out the window, okay? But if you want to know how the weather is changing, you've got to stick your head out the window, you've got to pull your head back in, you've got to wait 5 minutes, and then you've got to stick your head out a second time. To determine a change, you need at least two measurements, okay? And so that's what we're going to do here. In case A, what would I have to add to this short vector to the left to turn it into a long vector to the left? Well, I would have to add something, oops, I would have to add something to the left, and that's a straight line, okay? Now, again, what we learned in Physics 105 is that you would line these up tail to tail, and I would add a change, and there's the plus sign right there. Okay, this short vector plus this change gives me the long vector. On the other hand, if I wanted to turn a long vector into a short vector, I would have to add a change. Okay, there's the plus sign there. I would have to add a change to the right. Now, in the space, at right, indicate the direction of the induced magnetic flux in each of the loops. Well, now we're going to use right-hand rule number 3. Okay, because that current is going around in a loop, I'm going to use the curved part of my right hand to represent the current, and my thumb is going to be directed in the direction of the induced flux. Okay, so that's going to be the induced flux. And so that's going to be to the right in case A. If I do the same thing for case B, now the induced flux is going to be to the left. And remember what that means. Induced flux, that's the flavor that's caused by this induced magical current that suddenly appears in the loop, and I can't see the battery that's causing it. That's what we mean by induced current, and it causes an induced flux. Now, this part 5 is supposed to be at the top of the next page, and we just um, the the page the pagination just got uh, messed up here. So let's read it together. Is the direction of the induced magnetic flux in the same direction or the opposite direction to the direction of the external magnetic flux? Well, what they're asking there is for us to compare this induced flux to the external flux. And we see that in case A, the induced flux is in the opposite direction of the external flux. But in case B, the induced flux is in the same direction as the external flux. So in case A, it would be opposite, and in case B, it would be the same. Well, now we're asked, is the direction of the induced magnetic flux in the same direction or the opposite direction to the direction of the change in external magnetic flux? Okay, so going back here, this is the change in external flux. So we're asking, how does this induced flux, how does its direction compare to the direction of the change in external flux? Well, you see that in this case A, it's opposite. And in case B, it's opposite. And indeed, in every case that we are going to find, it will be opposite. And so that is something that you can take to the bank. Okay? Opposite. Opposite. And this is Lenz's law. Okay, that is Lenz's law. And for the life of me, I do not know why there's not an S there, but there evidently is not. So which of these techniques is useful in predicting the direction of the induced magnetic flux through a loop? Do we want to look at the direction of the external flux or the direction of the change in external magnetic flux? We want to use the change in external flux. Okay, the change is what's important there. Okay, if you look at the external flux, the induced flux is going to be in the opposite direction half the time. And if you only want to be right half the time, uh, go with that. But this is always going to work. This is always going to work. That's something that has to go in your toolbox. Okay. So now we have a discussion between two students. Student one says the induced magnetic flux through the loop always opposes the change in the external magnetic flux. Well, what do you think about student one? Well, I know what you think about student one, but what do you think about what student one said? Well, that sounds like what we just said, that the change in external magnetic flux was always opposite to the induced flux, always opposite to the induced flux. So that means that student one was correct. Now, my friend Jeff Adams and I wrote this tutorial because the tutorial in the published version just was not appropriate for the class. It had some mathematics that were not appropriate for the Physics 106 class. And so we thought that, maybe we should just change things up a little bit and let student one be right for once. Student two has the misconception that we were trying to fix in this tutorial. Student two says the induced magnetic flux through the loop always opposes the external magnetic flux. Well, no, that was true half the time, and in that case, it was just by accident or coincidence. So this is just not only, what would we call that? Wrong and sick and wrong. Okay, sick and wrong. Now, the induced currents in the loops cause them to behave like small bar magnets, which therefore causes them to experience magnetic forces as a result of the external magnetic fields. In the space at the right, indicate the direction of the magnetic force on each of the loops. Well, let's go back here. Hmm. There we go. So in the case of A, with the induced flux going to the right, that means it's acting like a little bar magnet with the North Pole on the right. Well, that North Pole is moving towards another North Pole, a strong North Pole, and they're going to repel each other. And so that's going to give me a force, a magnetic force, uh, to the left. And so in case A, that force would be to the left. Now, in the case B, my induced flux is to the left, and that means that this little loop is going to act like a bar magnet with the North Pole on the left and the South Pole on the right. Now, that South Pole is going to be attracted to that North Pole. And so the magnetic force would be to the right. Now, here's the point we're trying to make here. Use the above results to formulate a rule for predicting the direction of the induced current in a loop. Well, if I'm moving this loop towards the North Pole, this induced current is going to set up a little bar magnet such that it's going to fight the motion. This North Pole is going to repel this North Pole. And as I'm trying to move that ring towards the North Pole, it'll fight that motion. Likewise, over here in case B, when I try to move the ring away from the North Pole, I will set up this induced little bar magnet such that I have a South Pole next to a North Pole, and it will fight my motion. It will say, come back, come back. And, uh, and so when I'm trying to bring it towards the North Pole, it's like it's saying, go away, go away. When I'm trying to take it away, it's saying, come back, come back. And so that means the induced uh, dipole, and dipole is just a fancy word for the bar magnet, will oppose the motion. And that's always going to be the case when there is motion. It will oppose the motion. Now, on this last page, um, what we try to do is help you see that we have three methods now for finding the direction of the induced current. Now, I don't imagine for an instant that there's going to be a time in your career as a future dentist or doctor or um, whatever you plan to be, where you're going to need to find the direction of induced current in a copper coil. But the the model building that is involved in understanding Lenz's law is important, and that's why we do these exercises. But we have found three different ways to find this direction of the induced current, and hence the direction of the induced magnetic flux. And we just want to explore when those uh, three ways work. The first way that we uh, discovered was that we could use the Lenz force, QVB sine theta, and uh, and find the direction of that induced current. But that required that there be a velocity. When there was no velocity, there was no induced current according to the Lenz force. The second way that we um, came up with was this Lenz's law. Okay, this is Lenz's law, and that is that the induced flux was always in the opposite direction of the change in external flux. And we're going to find that that always works. Okay, the first method only works when there's relative motion, but this always works. The third method was this essentially a restatement of, uh, well, conservation of energy. If this induced current suddenly shows up magically, well, that's energy. And we know that energy always has to be paid for. And so that means I'm always going to be doing positive Verk to move that coil. And that means that this induced flux is always going to fight my motion, make me have to work harder. But again, this method only seems to give us a clear answer when there's relative motion. So let's look at a case where there's not relative motion. In this diagram, we have this stationary copper loop. The key word there being stationary. It's not going anywhere. And what we're doing instead is that we are increasing the magnitude of the magnetic field as time goes on. Well, try to visualize what that looks like um, as a movie. Well, what I would see is that early in the movie, there would only be a few field lines through the loop, maybe three. And then as the movie progresses, I would get more and more field lines going through that loop until I ended up with a lot of field lines through the loop. So if I were to use the idea that there is a magnetic force exerted on the charge moving in a magnetic field, um, would I predict that there's a current through the loop? And the answer is no. I mean, if V is equal to 0, then that magnetic force equation, well, that's zip. Okay. But if we were to use that general rule developed in number 8 on the previous page, and that says that uh, induced flux uh, is caused by a change in external flux. Well, yeah, remembering that flux is just the number of field lines that go through the loop, if I went, as we watched the movie, if I went from 3 field lines to the right to 20 field lines to the right, that's a change. And what direction would the induced current flow? Well, the induced flux, I'm going to write that in symbol form, is in opposite direction to the change in external flux. Well, let's do that, okay? I started out with external flux that was small and to the right. That's my initial external flux. A little bit later in time, I have a final external flux that is big and uh, to the right. Well, what change would I have to add to this short vector to the right to turn it into a long vector to the right? Well, I would have to add a change in external flux that's also to the right. This short vector to the right plus, there's a plus sign right there, plus this change gives me the long vector to the right. Now, if the change in external flux is to the right, then the induced flux would be in the opposite direction. Okay? That would be the induced flux. Now, how do I find the induced current from the induced flux? Well, remember, we're dealing with a wire loop. And so we're going to be using right-hand rule number 3. But this time, I know the direction of the flux or the field lines through the loop, the induced field lines. And so I use my thumb, which is straight, to indicate that straight flux to the left. And now my fingers are going to wrap around, curl around in the direction that the induced current will go around that loop. And so the induced current is going to go up the front and down the back. Okay. And it's that induced current that's going to cause this induced flux. Now, I know that the symbols look similar, but the induced current is just a capital I. Okay, it doesn't have this Greek symbol here, phi. It might be phi, it might be phi. I'm so old, I can't hardly remember. And now we ask you to read this statement here. We can use the idea that a force is exerted on a charged particle moving in a magnetic field to understand the interaction between the wire loops and solenoids in part 1. In each case, there is relative motion between the solenoid and the wire of the loop. In other situations, such as the one above, there is an interaction between the loop and the solenoid, even though there is no relative motion between them. There is a general rule called Lenz's law. See, we put the S here, but we didn't put it in the title. So uh, we're covering our bases. One of these is going to be right. There's a general rule called Lenz's law that we can use in all cases to predict whether there is an induced current and the direction of that current. Lenz's law is an application of the principle of conservation of energy to predict the direction of induced currents. The general rule given in number 8 on the previous page is a statement of Lenz's law. Below is a version from the book by Hellings, Adams, and Francis, College Physics Putting It All Together. That's the Brown textbook that we use in this class. Any change in the external magnetic flux through a closed circuit loop will induce a current in the loop that will flow in such a direction as to produce an induced flux that opposes the change in the external flux. Check to be sure that you understand that statement. And that's the main idea of this tutorial. I hope that this has been clear. If not, our lecture on Tuesday, we're just going to practice Lenz's law, practice, practice, practice. So hopefully, if things are still not clicking, that will help. I'm going to stop the share and I'm going to stop the recording.